and then working your way through some of the meaning behind the pH scale. So these are the answers to the questions that you're looking for. Block C. Didn't find any mistakes, so if you can find a mistake, that would be cool. I don't think I made any. Don't assume that just because Block C didn't catch anything, if you got something different than I do, don't assume that I'm right or that Block C is also right. They were pretty out of it this morning. Comments, questions, concerns. If you didn't get it done, don't just copy the, like, you'll be able to go back and do it on your own and then use the videos to check your work. If you want me to explain any of the answers, let me know. Going once. Yeah. Oh, I forgot about baking soda on there. Baking soda should be in here. Between the egg and the bleach. Thank you. Grapes, tomato, water, egg, baking soda, bleach. Thank you very much. See, I told you. Don't trust Block C, man. They were, first period was, they're pretty dead. Okay, ready to flip the page? 3, 2, 1. Okay, here we go. This is the second half of the questions. Same thing. I'll make a note about question 9 when we get down there. I did do question 9. I just did question 9 a little differently. If you want me to explain any of what I've covered, let me know. I did it this morning before class, so I was a little bit rushed. If you need me to flush out any of what I've written, let me know. And then for question 9, I didn't feel like cramming it into that tiny space. So I used the clues and I wrote down the appropriate pH down here on the bottom rather than filling it in on the chart up here. So I put the pH scale here. I labeled the 2, but I put the pHs for the rest of them down there at the bottom. You could say, so for blood is just slightly more basic than pure water. I said 7.5. You could put anywhere between 7 and 8. For the normal rain is just slightly more acidic than milk. I said 5.5. You could put anywhere between 5 and 6. Milk was a 6. But these are the values that that you're looking for. I think we'll raise that a little higher for you. Comments, questions, concerns. Going once, twice, thrice. So, look at cool. Flip the page again. Find me page says pH indicators. This is also a chunk I gave you for homework from before spring break. It was using these indicators up here and then giving you some specific values of pH and then taking a look at what the indicators are going to do. So tomato juice has a pH of 4, so using that and this chart up here, I determined that the colors of methyl red, methyl orange, bromthiamyl blue, phenolphthalein, indigo carmine, and litmus would be red, orange, yellow, colorless, blue, and red. Comments, questions, concerns on any of those? Again, don't just copy if you want you to do them. The chemical name and formula for the acid in carbonated drinks? Well, the acid is carbonic acid. The formula I gave you on the very first day I introduced to you the concept of acids, H2CO3, and the chemical name for H2CO3 would be hydrogen carbonate. It says, question 2b says to identify 6 properties that these two substances have in common. It's really just a summary of this page here. And so I didn't write it all down, but it's this column. Hydrogen carbonate or carbonic acid and lemon juice would share all of the exact same properties. They're both going to taste sour. Both acids are capable of burning you. You might not experience it the way that we typically think of burning. Like if I just squeeze some lemon juice on your hand, nothing's going to happen. But if I give you a paper cut and then squeeze lemon juice on your hand, you're going to feel it in a much more real way. The same thing with a carbonated beverage. Or if, we didn't have smartphones in the 90s and early 2000s, so we actually did stuff during lunch. One of the things my buddies and I would do was, because we were stupid, we would take orange peels and lemon peels, and if after you've eaten the orange and lemon, you can squeeze the peels and a little bit of juice comes out. So we'd run around and try and squeeze them in people's eyes because we were dumb. It's also flammable, which is cool too. So you squeeze it, light the lighter. But yeah, you get some lemon juice, you get some pop in your eye, it's going to burn. And the reason it burns is because it's acidic. Same thing if you've ever laughed with milk in your mouth and then the milk comes out your nose. The reason it burns because milk is slightly acidic. That's a very sensitive area in your body. You don't want lemon juice, pop, milk coming out your nose. It will burn you. We don't typically think of it burning like sulfuric acid will actually dissolve a human body. If you've ever seen Dante's Peak. Great movie from the 90s. The 90s was big into disaster movies. You can watch an old lady dissolve in a lake of sulfuric acid. It's pretty awesome. The indicator test is going to be the same. Litmus is going to turn red for both lemon juice and pop. It's going to corrode metal slowly. I mean, those aren't very strong acids, but it will do it. They're both going to be conductive. They're both going to have a pH less than 7. They're both going to produce H+ ions. That's the table. Those are the similarities you're looking for here. And then in question 3 says, acid-base indicators not just found in science labs. Find a natural acid-base indicator. So you have to go online. You have to Google something. Did anyone find anything? I found 2. I mean, I found 6, but I wrote down 2. Did anyone find a natural acid-base indicator? Cabbage juice. Specifically, what kind of cabbage? Red cabbage, you betcha. That was the first one I wrote down as well. And red cabbage juice will be red in an acid. It'll be purple in a neutral solution, and it will turn yellow in a basic solution. Did anyone find any others? Red cabbage is the most common one. But did anyone find any others? The second one on the list is turmeric. Some of you may have this in your spice cabinet at home. I know I do. Turmeric is a yellow powder. In an acid and in a neutral solution, it'll stay that yellow color. But if you put turmeric into a basic solution, it'll turn orange or kind of a reddy brown, depending on the strength of that base. So turmeric is another thing that you can use as a base indicator. Also for cooking, because turmeric is yummy. Comments, questions, concerns on this page? There were more of these in natural indicators. I think on the list I found had 6 of them on there. The question did also say, describe the pH range in which color changes occur and state the color changes. So that's what I did there. Okay. The next page looked like this. This one was another exercise in specific substances, identifying their pH value, identifying acid and base. You can take pictures if you want, but you don't need to because this will all be in the video when I post it. And then how methyl orange, brom thymol blue, litmus, indigo carmine, phenolphthalein, and methyl red all change in these different compounds. Again, if you didn't do your homework, shame on you. I give you lots of time to get it done, and you had 2 weeks. You're not going to learn the things if you don't practice the things. Comments, questions, concerns on this page? And if you got something different than I got, don't assume that you're the one that made the mistake. Once, twice, thrice, sold. And then this is the page I gave you yesterday. Acids versus bases. Here you go. This is just the table. Again, properties of acids and bases. The definition of an acid and the definition of a base. I didn't write it all down, but here it is. This acid is a solution that produces H plus ions, or a compound that produces H plus ions in a solution is the definition of an acid. The definition of a base is a compound that produces hydroxide ions. The pH of an acid is less than 7, a base is more than 7 in the chemical formula. For an acid, you're looking for H. For a base, you're looking for OH. Production of ions is going to be H plus and OH minus. They're both conductive. The taste is sour for an acid, bitter for a base. They will both burn you, but the base will taste slippery as well. And then I've given you tons of examples. Yes, Brooklyn. That was the, so I pointed you towards the general formula for acids and bases. Specifically, because the A and the A and the HA and the B and the BOH, just, they can be anything. They can be, if in a, for example, in a base, it could be Na, and your base is then NaOH. The important part of the formula to look for is the H and the OH. And then the list down there at the bottom, classify each of the following as an acid or a base. It goes acid, base, base, acid, base, acid, acid, base, acid, base, base, acid. Comments, questions, concerns? Class? 27 students, man. And we're missing 5 today. Okay. Hearing nothing, I'd like you to flip the page. If you recall, way back, when I introduced the concept of acids, bases, I also said we were going to talk about acids, bases, and salts. Now there's a reason why we lump salts in here, and we're going to talk about it today. So, when you think of salt, what comes to your mind? I've been referencing salts on and off this whole chapter. What do you think of? Sorry? A white pebble. Where are you finding this white pebble? That's what you think of for salt? Okay, salt water. Or seawater. Seawater is salty. If you've never had a chance to swim in the ocean, don't get it in your eyes. It's not a comfortable experience. And you can actually, for those of you who have swum in the ocean, what does it feel like after you've gotten out of the ocean? It's like tingly? It dries out your skin. Why does it dry out your skin? Because so you're covered in salt water, you get out of the water itself evaporates and the salt stays on your skin. If you want to kill snails and slugs, we put salt on them. Why? It dehydrates them. Basically, it dries them to death. So, I mean, swimming in the ocean does the same thing to your outer layer of skin. It pulls the water out of those cells, dries your skin, or dries out your skin. Okay, so seawater. We think of salt when we think of seawater. What else do we think of when we think of salt? Yeah. Seasoning. Yeah, salt on food. The salt on food has a name. What is it? We typically call it what? We typically call it salt, but if we were to expand that, it would be We'll get there. Typically, we call it table salt. We specify that it is salt found on the table. And someone gave us the name already, sodium chloride, NaCl. So when you think of salt, you think of typically we think of what the salt that's found in the water. We think of salt that's found on seasoning, table salt. But there's a reason why we specify that this is table salt, because not all salt is going to be found on the table. There are other salts out there in the world. Even when you think of table salt, there's different kinds of table salt. What kind of table salt do you use in your home? You're one of them. My daughter's a huge fan. My mom does it too. The pink Himalayan sea salt. My daughter, I want pink salt. I want Noni's pink salt. I want the pink salt. And so my wife and I had to then go out and buy the pink salt. Yeah. Pink Himalayan, if I spelled that properly, salt. Pink Himalayan salt is also just NaCl, though, generally. So why is it pink, but NaCl is not pink? Table salt, if you just use generic table salt, what's its color? It's white. If you look at, does anyone ever looked at it under a microscope? Did you do that in middle school? If you look at a salt crystal under a microscope, you'll actually see it's colorless. It just gets white because it's it gets scratched in the way the light bends through the rest of the crystal. Makes it look white, but it's largely, pure salt crystal is going to be largely colorless. So why is Himalayan salt, if it's the same chemical formula, why is it pink? I hope not. Okay, so C Block asked about this, so we did some Googling. Here are the answers to the Himalayan sea salt or the Himalayan salt question. I'll zoom this bad boy in here. I'm going to add some notes up here at the top. So chemically, you go down to the ocean, you get a big bucket of water, you boil out the water, you'll be left with a white crystal substance. That's table salt, NaCl. You go up into the Himalayas, the same thing, except it's going to show up pink. It's the same NaCl compound, but why is it pink? Here's why. Himalayan sea salt is between, or not sea salt, but Himalayan salt is between 96% and 99%, depending on where you get it, NaCl. So basically, it's the same thing. Table salt is more than 99% NaCl, but it's not 100% NaCl because we add things. Does anyone know what we add to table salt? Did you say it? There is something. If you look at the box of table salt. Has anyone looked at that? There's usually a word out front. Starts with an I. Yeah. If you look at a box of table salt, you go to the grocery store, you go to your cupboard at home, it'll say iodized. And that's because the reason for that is, as a species, there are compounds that we need in very, very small amounts, iodine being one of them. If you recall back to one of the demos that I did for you before spring break, iodine was also the purple smoke coming out of the clock. That would have been deadly in large quantities, but in small quantities, we need iodine. So table salt gets iodized, gets a little bit of iodine added to it. Himalayan salt has other things added to it naturally in the environment, which is why it's pink and why it's not 100% NaCl. The things that get added to Himalayan sea salt, if it's 96 to 99% NaCl, that means it's 4% to 1% the following compounds. The biggest one in there is calcium. The next one is iron, which is what's largely responsible for the pinkiness of it. But if you actually look at pink Himalayan salt, it's not the same color pink all the way through. All of the crystals are a little bit different, and that's because that everything in there is going to have slightly different percentages of these things. So we've got calcium, we've got iron, we've also got zinc in there. There's some chromium in there. For those of you who are interested in cars, chromium is what makes hubcaps shiny. Chrome. So we've got calcium, iron, zinc, chromium, magnesium. which you've seen in class. Magnesium is that kind of dull silvery color. And there are sulfates, so SO4 minus 2 compounds in there as well. The most common ones, are these first three, from what I read. And these are the ones that give it that pinky color. But largely, and this is why, I mean, I have never noticed a taste, because salt's job is not to give something else its own flavor. It just enhances the flavor of what's already there, apparently. But there's this sensation of saltiness, and that's going to be the same everywhere. So I've never noticed a difference in the taste for pink Himalayan salt, but like I said, my daughter's obsessed with it. Okay, so typically when we think of salt, these are the answers that I get. I could show you the same page from a couple years ago, and it would be largely the same thing. Often there are three other things that get listed when we talk about salts. Florida hasn't been in the news lately, but there was about 10 years ago. I think it was about 10 years ago. Maybe a little bit more recent than that. Salt was in the news in a big way, coming out of Florida. Does anyone know what I'm referring to? Anyone think back? Oh, it was on the news. It definitely was on the news. There was a class of drug known as, people were taking them as bath salts as a drug. And then it hit the news. A Florida guy, like a homeless dude, murdered someone and was eating his face. He was on bath salts. Or Epsom salts. Some of us, if you're physically active and your muscles are sore, you want to take a bath that relaxes the muscles, you put Epsom salts in there. So there are other salts that we consume or use that have different properties. You're not going to put Epsom salts on your food, you put them on your feet. There's also salt lamps, salt crystals that we put the light on the bottom and it shines different colors. So salts show up in a bunch of different ways. So we need a proper definition for what makes a salt, because we can't just say table salt anymore. So here's our definition. In chemistry, a salt is an ionic compound. Ionic compound means what? If something is ionic, what do we know about it? It's a non-metal and a metal. Good. So if we look at table salt's NaCl. Na is sodium, it's the metal. Cl is chlorine, it's the non-metal. So a salt is an ionic compound produced through the reaction of an acid with a base. And I'll show you what I mean. So the reason that we lump salts in with acids and bases is because a salt is any compound that you can produce by reacting an acid with a base. And that reaction has a name. We call that reaction a neutralization. And neutralizations are really quite interesting. Let's take a look at them. The next couple of days, what we're going to look at is we're going to move forward and we're going to look at a bunch of different kinds of reactions. I think there's 6 of them. There's 6 different classifications that we're going to look at. There's more than that, but these are the most common 6. And the first one that we're going to look at, we're going to start today looking at acid-base neutralizations. So, a neutralization. Neutralization is the name for the reaction between an acid and a base. When this reaction happens, the products are a blank and blank. While the products are a salt, always, that's how we define a salt. We define a salt as being the product of a reaction between an acid and a base, but something else always also gets produced. And so what is that thing? I won't tell you. Let's take a look at it and then come back and fill that blank in a second. A couple examples. First one is this. If I've got HCl and I've got KOH, on its own, if I take HCl as a solid and I dissolve it in water, you're going to get something you've already seen before. You're going to get this. Those of you who did the lab, you take an HCl crystal, you dissolve it in water, and you get an unknown concentration of HCl. Looks a lot like water because it largely is water, but there's extra things dissolved in here. There's hydrogen ions and there's chlorine ions dissolved in this thing. And you take KOH. KOH is another, well, the other one we have on the table is NaOH. But you take KOH, the crystal, you dissolve it in water. Individually, the KOH in water is going to split up into K plus ions and OH minus ions. So this guy is going to become the H plus and the Cl minus is going to float separately with each other on its own. Before you mix it with anything, that's what it's going to do. It's like when you make powdered juice at home. Or my daughter, or we drink powdered iced tea. You take the iced tea crystals, you dissolve it in the water, and they disappear. The act of them disappearing is the bonds between these guys breaking apart and just kind of floats around. If you wanted to get those crystals back, you could just boil the iced tea. The water would leave, and it would recrystallize that powder at the bottom of the pot. They would come back together, and they'd form a solid. The same thing is true of the KOH. The K becomes an ion of potassium. The OH, that's a polyatomic ion, but the polyatomic ion is going to stay together on its own and become OH minus. And now before the break, I showed you, I used a meme to show you guys how this kind of happens. The meme I used was the distracted boyfriend meme. And so if you take a look at what happens here, on its own, H and Cl, totally happy. You bring in K plus and OH minus, and now all of a sudden a formerly happy couple is going to get distracted. And you get the boyfriend meme. Instead of recombining with the Cl minus, what is the only other thing the H could join with? The other negative thing, the OH. So this guy and this guy are going to combine. Well, when you combine H with OH, what do you get? You get HOH, which we also call H2O. And so the thing that you're looking for in a reaction with an acid and a base is to identify, do I have an acid? Is there a hydrogen-loaded compound? And is there a hydroxide-loaded compound? Because when you combine them, the hydrogen and the hydroxide are always going to make, what is that? Water. Always, 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 water will be produced. And that's that blank right there. Water is always the first thing that's going to be produced. And then we've got to figure out, okay, now, if a salt is what's produced between an acid and a base, and I've already got my water, my other product, what is the salt going to be? Well, let's look at the other ions that are present. I've got K plus and I've got Cl minus. When these two come together, what are they going to do? They've been abandoned by their other halves, and so they naturally are going to find each other. If you were the last two couples on Earth and one cheats with the other, well, then you've only got one option. What's going to happen? And make what? Someone said it. They are going to come together and make what? KCl. Why is it KCl? Well, who said KCl? Which of the Brooklyns said it? Okay, why? Why did you say KCl? Yep, the positive one, the one that's out front, gets named out front. The one that was out back gets put out back. Why is there only one of each? Why is it KCl as opposed to K2Cl or KCl2? And this is where we got to be really careful. What determines how these guys come together? Sorry? Yes, the negativeness and the positiveness of it. So this guy has a charge, Cl has a charge of -1, K plus has a charge of +1. So because they have the same charge, I only need one of each for them to become electrically neutral. An ionic compound, it's more than just a metal and a non-metal, it's a positive and a negative, and those things have to balance. Cool. So when HCl and KOH react, you're going to get water and KCl. And that's going to be true for all of these acid-base reactions. Let's take a look at them. Next one. I've got H2CO3 and I've got MgOH2. So I've got an acid, carbonic acid. This is the acid found in pop, soda. MgOH2. This is called, as a base chemically, it's called magnesium hydroxide. Commonly, you go to Save on Foods or Whole Foods or Freshco or pick your grocery store. This thing's called milk of magnesia. It's an antacid. You can buy this. When you take your pop and you take your milk of magnesia and you put them together, what are you going to get? Well, every acid and base reaction is going to have the same initial product. The H2 and the OH2, all of the H's from the acid, all of the OH's from the base are going to react to produce what? Someone say it loudly. When you take hydrogen, you react it with hydroxide, you get? Someone said it back there, water. H2O is always the first product. And now we've got to figure out what's the salt that is produced here. Well, look at the pieces that are left. I've got Mg and I've got CO3. To figure out how that salt gets built, because this is an ionic compound, we need the charges on those ions. What's the charge on magnesium? It's +2. What's the charge on carbonate? It is -2. I saw some students pull out their polyatomic ion charts. You are always absolutely free to do that. There is a shorter, more quick way to do it if you'd like. Charge on H is always what? 1. The charge on OH is always 1. So however many H's you need, you can use to figure out what the charge is on the other thing. I need 2 H's to balance out my CO3, so the CO3 has to have a charge of 2. I needed 2 OH's to balance out the charge on magnesium, so magnesium has to have a charge of 2. The magnesium is the metal, so it's going to be positive. The polyatomic ion is always going to be negative. So that's a quick way you can do that. Okay, so I've got H2CO, my H's and my OH's became H2O, and now I've got to create the compound here. What's the salt then going to be? If Mg and CO3 have the same charge, the compound's going to be what? It's going to be MgCO3. And now if we wanted to, we could go ahead and do what? Balance it. I've got H's, I've got C's, I've got O's, I've got Mg's. I've got H's, I've got C's, I've got O's, I've got Mg's. I'm not going to, but you're going to have to go back and spend some time doing some balancing for me. Okay, let's do another one. I've got question 2. CH3COOH plus CSOH. Do I have an acid and a base? This is the tricky one. There's obviously a base. The CSOH, there's hydroxide. What's this first one? It's acetate and H. This is the one where I told you sometimes it's going to be written with the H out back. It's the one exception to the rule. It's acetic acid, also known as vinegar. So the H from the acetic acid and the OH are going to make H2O. And what do we have left over? The CS. The CS is going to have a charge of +1. The acetate is going to have a charge of -1. So what is the salt going to be that gets created in this reaction? CsCH3COO. It's this whole polyatomic ion and the cesium from the CSOH. Now this particular salt you're going to want to stay away from because cesium is radioactive. As a general rule, this is not something you want to put on your French fries. It will kill you. Next one. We have 3 more, even though there's only 2 more listed. First product is always going to be H2O. All of the H's from the acid, all of the OH's from the base are going to work together to create water. So then what's left to form the salt? The Na and the PO4. Now to build the salt, we need the charges. What's the charge on Na? There's only one group of OH. OH has a charge of -1. So Na has a charge of +1. What's the charge on PO4? It's going to be -3. There are 3 hydrogens that are going with the PO4. Excuse me. So the PO4's got to be -3. So when I'm building now this salt, which is used as a fertilizer, what am I going to get? We have to do swap and drop. It's going to be Na3PO4. Very good. Question 4. First product is always going to be H2O. That's all of the hydrogens from the acid, all of the hydroxides from the base. Now, I want to build the salt. I need the charges. What's the charge on NO3? If there's only one hydrogen with the NO3, the charge has to be -1. If there was 2 hydroxides with the calcium has to be +2. So now when I build this thing, we're going to swap and drop. What are we going to get? Yes, NO3 in brackets and then a 2. Very good. Just for fun, let's do one more. I'm going to put it over here on the side because this is actually the reaction that you guys did on the which acid is more, or which sample is more acidic lab. This is the reaction that you did. You took an unknown concentration of HCl and you added to it NaOH. Now, on its own, these two are both fairly dangerous compounds. But if I asked you to go get some HCl without leaving the classroom and without coming to my chemical table, where could you find HCl? What's a common name for HCl? Tie it back to what I introduced it to you as the very first day we did acids. Your body produces this acid. It's a stomach acid. HCl is stomach acid. If I asked for some stomach acid right now, what would you do? Throw up. Yeah, you shove your finger down your throat, and now you throw up, and now you've got HCl. We go to the bathroom, we pull out the bleach, now we've got some NaOH. On its own, these two compounds are not pleasant compounds. But when you mix them together, what do you get? The first product that will always be produced in the reaction between an acid and a base is H2O. So that takes the hydrogen from the hydrochloric acid and the OH from the bleach. Now what's left? Which is more commonly known as what kind of salt? Table salt. So you throw up into a bottle of bleach, and what do you get? You get water and you get table salt. I mean, yes, there's other ingredients there in the bleach, but if you think about what this means, this on its own is going to make your life absolutely miserable. This on its own is going to make your life absolutely miserable. You did the lab where you took hydrochloric acid. Actually, the strong one was sample number 2. Where's sample number 2? You take sample number 2, you take a bottle of NaOH. On its own, either of these will mess you up. Probably won't kill you, but it will be wildly painful. You're going to the hospital, chemical burns. You mix them together, what do you get? Something that's entirely drinkable. Water and NaCl. It's gross. Has any of you ever had to drink salt water? For a sore throat, you gargle with it. Yeah, your tooth comes out. When I got my wisdom teeth out, we're supposed to gargle with salt water. This H2O and NaCl is disgusting. It's not going to kill you. You can drink it. But individually, at least painful, if not deadly. So they'll say, so we could have taken the flask and just drunk the flask from the lab that you guys did. The short answer is yes. The long answer is phenolphthalein is toxic, and you added phenolphthalein to turn the thing pink, so you could see when the reaction was done. This will give you cancer, so no, you're not drinking the flask. But you take the phenolphthalein out, and if you can get it to the point where the HCl and the NaOH are perfectly balanced, yeah, you have salt water you can drink. It's interesting. Like the implications of some of these reactions I find very interesting. Now, I'm going to be the first to advocate that you don't do this at home, because getting that proper balance is not necessarily the easiest thing. But if you can, you then could. Okay, that's salts. Quick lesson. Here's what I want you to do. This page, nice and easy. I just want you to identify whether the things you have are acids, bases, and salts. And you have to look at the formulas or the names to figure out what is what. I want you to do this page. Flip the page again. This is where things get more interesting. There are 14 reactions on this page. What I would like you to do, for question number 1, I would like you to complete all of them. So give me the products for all of them. And because it's been a while, I want you to balance letters A, C, E, and G. Once you've created the products, balance those equations. You're going to need some extra paper, perhaps. You might want to work on the whiteboards for this. But I want you to complete all of them, but then go ahead and balance A, C, E, and G. And then for these guys down here, what I'd like you to do is, you do not have to balance these ones, but you need to complete the following acid-base neutralization reactions as both word and formula equations. The easiest way to do question 2 is to take this, turn it into a formula, give me the products, and then go back to the name. I'll show you what I mean. I'm just going to do the work down here. All of these acids I have given you formulas for on the acid-base introduction pages. Sulfuric acid is H2SO4. Potassium hydroxide is KOH. You should be able to come up with these formulas relatively easily. Hydroxide is always OH. You're just building the chemical formula. Now, when I go ahead and give the chemical formulas for the products, the first one's always going to be H2O. The second one is going to be what in this case? Sorry, Brooklyn? Almost. K2SO4. because the charge on K is +1, the charge on SO4 is -2. And now we go back and we say, okay, what is the word equation then for what we just made chemically? Well, H2O is just water. What's the name for K2SO4? Let's go back to the naming rules. Potassium sulfate, good. You don't need Roman numerals because potassium only has one charge. In fact, I don't think you're going to need Roman numerals on any of these, but that's just a fun little bonus. But that's what I mean. Go from the words to the formulas, make the formulas, go back to the product names. Yeah? At least one, yeah. Could be H, could be H2, could be H3, but yes. But I've given you, so I don't expect you to come up with these formulas. I've given you what the formula is for sulfuric acid. I've given you the formula for acetic, phosphoric, nitric, and hydrochloric. On this page, right there. They're all right there. Hydrochloric, sulfuric, nitric, phosphoric, acetic. Is that all of them? That's all of them. So just you reference the formulas I've already given you for the acids, and you have to build the rest. You've got about 20 minutes on your market set, go. You have your task.
I have a quick question for you.
Yes.